grew up on a farm in central Iowa, and I left the farm and went to school. Eventually I went to grad school and got a PhD in chemistry. Then I went to work for a couple large organizations for about 30 years. Well, along the way, I had a couple of things that changed my life about what I wanted to do with it. First one was when I was a sophomore in college, and we just learned how to distill things in organic chemistry, and a professor of mine wanted me to distill some nitrobenzene. And so I set it up like we set up in lab. I began to distill it, and I picked up the jar and I looked at the label and I saw skull and crossbones. I started to read the safety issues about it. The stuff is very toxic. You know, it gives you leukemia if you get too much of it. So what I realized at that point is they didn't know anything about safety. You know, it wasn't on their radar. So for the rest of my chemistry career, I always took care of that myself. Well, along the way, about 30 years later, I discovered I have a sensitivity to formaldehyde. And it's an old house, it's got an underlayment, it's outgassing a lot of formaldehyde. At that point, I realized that there had to be better ways to do these things than to have all this toxic, stuff around. And we wanted to build a house, and so we started to look at natural housing. And after looking at a lot of different things, I finally decided that straw clay was the best for our climate. And then I found people like Lou and some people in some other places and began to learn about it. And what I discovered was I wanted more information than what was there. I didn't think it was developed enough to satisfy Doug. Now, Doug always wants to know how and why. So this is about how and why for straw clay. When I started looking at natural housing, I wondered, what in the world are these like? Are they real different? You get this idea about, mud huts and so on, because you're using natural materials. Well, I just wanted to show you some pictures. They look like stuccoed houses of one kind or another. You've seen these kinds, but these are all straw clay. That's what's in the walls. And of course, the finish with straw clay is it's flat. You could even put drywall over it if you really wanted to, but that, be a real loss. So they look very much just like a normal house, with the exception that a windowsill, is going to be deep. It's a nice place to sit on or put flowers or whatever. And because they're beveled in like this, you don't really notice that the wall's that thick. What I want to look at today is these topics: straw and clay as construction materials. You're building a house. You're spending thousands and thousands of dollars. It's natural materials. That doesn't make them perfect. You still need to have a specification for your materials, because those are construction materials. You also, of course, want to know that what you're using works. So we have the topics of design and the properties testing that we've done, and how do you produce the straw clay insulation at a job site, and then what's the operating window for doing this. Everything has an operating window. You don't set your lawnmower too low, you don't set it too high, you set it where it works. Well, in construction you also have that too. In our specification for clay, we have to have a test. We need to know what we're working with. Now, the subsoil that we use, of course, have clay, silt, sand, rocks, and we have to take a sample and get a test. Why? Because in our experimenting and testing, we found out that you've got to have at least 40% clay in that subsoil. If you don't, your wall integrity suffers. And so we have that requirement. And one of the issues being is that the clay and the silt are different. Clay is a very polar surface, as Lou talked about, really attracts water. Silt doesn't have that polar surface. And so the more silt you have, it actually uses up the clay function, and we want that clay function for the straw. So you want more of the clay, less of the silt. That's why you have the requirement. There are tests that people have put in books, put it in a jar, put the water in, shake it up, let it set, read the levels. Very inaccurate. You can also take a sample of the subsoil, and you can make a rope, and you can bend it and see if it cracks. And people say, well, if you can make a circle, then you've got 80% clay or whatever. Also not true. So you want a lab test, and they're less than $30, and you're spending thousands. It's a nothing. These are just various kinds of ratios that you might find in subsoils. So they range all over the place. You've got to find a source. We find a local source as best we can, because there aren't places that make bricks anymore. There used to be a lot of places around the Midwest made bricks, and they had a clay source. Well, those are shut down, or people don't know where they're at, so you do have to hunt around. And it might be as simple as the local school building after they dug the foundation. If you can find blue clay, that's great stuff. As we talked about, clay is sticky, and it's sticky because it has this polarity on the surface. And it also has stickiness because of what kind of metal ions are in the clay. And it has a very high surface to volume ratio because it is so small. So if you look at clay, silt, and sand, clay goes up to 2 microns, which is a foreign word, I'm sure, to most people here. That is like 10s, hundreds, thousands, 10,000, 400 thousandths of an inch. Okay, it's small. Okay, your naked eye can see down to something like 40 microns. Can't see below that. And so, clay stops at 2 microns. Silt goes 2 to 75 microns, so you can't even see a lot of the silt. Those particles are that small. And if we, what we've done here is that if that little dot is 2 microns, then the largest silt particle is ratioed like that. There's a lot of change, and of course, if you take that big one and you make all these small ones, you have so much more surface area. So the surface area plays a factor. Now, what are clay's properties? Well, it's an adhesive. Okay, so you stick it on the straw, you pack it in the wall, it acts as an adhesive, it holds it together. So between the fibers and the clay, you have integrity. If you want to break the wall apart, you have to work at it. It won't just fall apart. I make wall sections 2 by 2. When I want to open them up after they're dry and look inside, I have to hit them, quite hard in order to break them apart. The clay prevents the straw from absorbing water. We'll show you that in a bit. It also protects the straw from fire. The rodents don't like it. The insects don't like it. So you get 4 different things from putting some clay on the straw. They're all important. Some clays will have some odor. Okay, if you ever find clay that has an odor, you don't want it. It's because it has organic material in it, and there's anaerobic decomposition going on. So you're smelling, like hydrogen sulfide or something like this. So you want to stay away from that. Clay also, of course, has thermal mass, which is the other way we help hold heat in a house, besides the R value. Now, if you were here for loose talk, we talked about humidity and how it controls the humidity in the house, and that's true. The clay really likes that moisture, and so if the humidity goes up, the clay just pulls it out of the house. And then if the air gets real dry, it releases it back into the house. So as Lou talked about, you stay in this comfort zone of humidity, like between 35 and 65% humidity. Well, if you get 80 degrees in the house, 65% humidity is still not bad. And most of the time, you're going to be way below that, and the house really feels like it's air conditioned, even though it's not. You have no equipment to take care of, no bill or anything. The clay also is something that expands when it picks up the water. Clay actually forms a structure with water. Okay, that's why they can put it in a lagoon, as a liner in the bottom, because the water can't get through it. It really likes water, but it forms a structure with the water, and it prevents water from passing, further into the clay. So water goes through it very slowly once it gets wet. Well, there's an expansion that goes on. So let's say you put clay plaster on the outside of your house. Well, when it gets wet, it expands. Any little crack gets pushed shut, or around the windows. You know, it pushes up against the wood. So they actually find that, you know, you don't get wood rotting around, you know, the window trim, because you have this function going on. And we already talked about the last one there. The straw is also a construction material, and these are the specifications that we currently use. It should be golden in color. Why? Well, nature has a recycle process. So if I cut the straw, it was gold to begin with, rains, now nature starts its recycle process because the dormant microbes that are on the straw, because it lignified and you know, went dry and wasn't green anymore, they wake up and they begin that process. So you don't want decomposition, you want the straw to last that 700 years, which it can. And so if it's not the right color, it's junk. It's not construction material. Now, wheat or rice or barley are the things that have historic use and we know work. We do not have any scientific data on other types of materials, so we don't use them. You want something that's stiff. You want the air pocket inside the tube. You don't want something that's flat like a grass. You want that air tube inside, and then of course the air pockets between the straws, and that's what gives you your insulation in the wall. You never want any green material. Anything green is food for microbes. You don't want dirt in it. Dirt is food for microbes. And so once it's baled, you want it under a roof. You want it kept dry until you use it. Now, straw, you think of straw, and you know, I grew up on a farm. Oh, that's like bedding, you know, bedding for cows and so on, etc. And I never think of it as being a durable material until I got involved in this. And then I realized, okay, it's cellulose, wood cellulose. Okay, they're two different forms. One's solid, one has all this surface area. The difference in rate of decomposition just has to do with that large surface area versus something that has a lot less surface area to volume. But it's just as durable if you can keep it dry. And so in our case, we use the clay to keep the straw dry in the house. So if you look at this, you see there's a bright bale she's pointing to. That's the good stuff. The rest of it's like, you don't want to use that. Okay, there's a pile that we can use all of that. That's good. And we tear these bales apart and we put them in this mixer. Once in a while you find there's some green material in there. There's a weed or something. You just throw it out. You don't want any of the green material. There's the 700-year-old straw. An architect over in Germany, which we went and visited, allowed us to look at that. He had harvested that out of a remodel project, I think it was. And anyway, it's like, that's 700-year-old straw. Gee, that looks like the straw we just looked at. It's golden in color. It's kind of hard to think about that, you know. How many 700-year-old houses are there in the U.S., period? Originally, this work, this process was done over in Germany, and there was work done by a fellow named Minke, Earth Construction Handbook. And when he looked at straw clay, his conclusion was that you could only get to down to like about a 40 pounds per cubic foot or denser wall. You had to have that much clay. And the R value of that was only 0.8 R per inch. Well, that just wasn't enough insulation for our 9,000 degree heating climate. We need, you know, an R20 wall, and, you know, 0.8 times a 10-inch wall would be an R value of 8. Well, that's not going to cut it. So we thought, well, you know, there is a ratio. Okay, we wanted to go to 1.7. That would give us an R20 for a 12-inch wall, which was like the standard wall for straw clay. What we needed to do in order to, you know, achieve that is we needed to demonstrate that the clay would protect the walls from moisture. Because the conclusion in the literature was that If you didn't have enough clay, you were going to get water damage, you were going to get rot. And we were going to put a whole lot less clay on this than they were in order to get the R value we wanted. So then we also needed to make this viable for construction, so we needed to develop a processing equipment to go with that. So we needed the technology, that it really worked, as opposed to what was in the book, and we needed the equipment. To do this, I began to make wall sections. These are just 2 by 2 and they're 12 inches thick. It's like taking a chunk out of a wall where the studs are 2 feet on center, which is the way we do this. And then, for detail here, the one on the left is straw only. The one on the right is straw clay. 13 pounds per cubic foot, not the 40 they were doing, 60, but 13, okay? What you see is a slight change in color. That's all you see. All there is there's a number of layers of particles on the straw. And you actually have an equal amount of weight of straw and clay in that wall section. That's an up close. As you can see, there's just a small change in color. But it makes a huge difference. The R value, as you can see from this chart here, we're clear up on the left side as you look at that. We're up around 1.7. We even had some 1.8s. And that's at 13 pounds per cubic foot. That's where we want to be, okay? And as Lou had shown in his talk, the testing at the laboratory showed that we got that R value. That's not a calculated R value, but by the way, all of our data fits right on the line of the data that was generated in Germany. They have higher pounds per cubic foot and they have R values, and the line connects. It just goes all the way up. Ours is just a continuum of what they did. So it's consistent with what they were measuring. This is the way a wall dries. It dries very fast at first if you're in the summer. Now, the other line is more flat, Madison 5. That was made in October when the temperature at the height of the day was 50 degrees. Okay, it's not going to dry as fast. Well, in your refrigerator, you put something in there because the microbes don't work very fast once it cools down, especially below 50 degrees. So it doesn't really matter if you make this when it's cold and it dries slower, because of the temperature drop, the microbes aren't busy. They go into dormancy. It's too cold for them. So it doesn't matter what time of year you do this. Of course, working when it's 35 degrees out with water, not too many people will do that, but it's fine if you want to. Looking at this chart, which is just, it's the same data, it's just put on the chart in a different way. Okay, so this is what percentage of water has left, 0 to 100%, and this is dates going across the bottom. At 4 weeks, typically 50% of the water that you put in there in order to get the clay on the straw is gone. But it actually takes a year for it all to leave by weight. How fast it leaves doesn't matter. It does matter, of course, that you want, because you want to plaster at some point, so you have to wait for a certain length of time, and typically people wait 3 months of drying before they plaster, and then we know that works. Okay, we have looked at 1 month, and we have to do some more looking at that to be sure that that's okay. So the drying thing does affect how soon you can plaster the walls, but it doesn't affect the quality of the wall.
Can mechanically drying it, fans, dehumidifiers help?
You have to, yeah. You can't close up the house. When you put the insulation infill in, you got to leave out the windows and the doors, at least the windows, because you can't have that humidity build up. If you let it build up in there, if you close it up, you're going to get white mold on the surface. Okay, you got to let that air out, for over a month before you close that up, because the moisture has to get out and go somewhere.
Are your forms left in place when you're waiting for the drying?
The forms that are used in the construction that make the cavity that we fill, those come off the day of construction, the day you fill. Yeah, about 1 to 4 hours, and you take, when the wall's stuffed, you don't have to wait any more than about 1 hour, and you can take them off. Typically, they're going to be on there a couple of hours, and then you take them off. It doesn't. It isn't hard like it is when it's dry at that point in time, but it's set enough that it will stay put. So then you take the wood forms off and it begins the drying process.
And are you restricted from putting like exterior siding or interior wall finishes on during that period of time, during the drying time?
During the drying, the surface has to be left open. At 3 months, you're safe to go ahead and do whatever, okay? But we're trying to find out if 1 month is enough. And that has to do with the moisture is coming out of the wall at a certain rate. Changes into vapor, comes out of the wall. If you put something out here as a barrier, but if it's, say, like earth and plaster, which also has a permeance or the ability to let that vapor continue out at the same rate, it's not a problem. The problem is if you have something there that slows down its rate of travel, then it collects. Then you get into the higher humidity, you get into the moisture, you get into the microbacteria. Now, at first I made wall sections and I waited a year and then I'd open them up to see, that what I put in the mix, was it better or worse? And then I realized, gee, all I want to know is whether or not I have a compost pile or whether I have a good wall. So I put a thermocouple in there. And this is what you find. And what you find is there's an initial temperature spike, but it only lasts about 7 days. And then it's gone. And it's not large. And then, of course, when you break it open, you see almost nothing. There's no structural damage. There may be a slight coloration change, but otherwise than that, there's nothing. And we have a dry wall section. You can come and look at it yourself. It's over by our demo in the tent.
What makes the temperature spike?
You bring in microbes on the straw. I mean, they're there. They're in nature. They're always there. And you've now wet that straw for the first time since they went dormant. And they go, okay, time to go, recycle time. But what happens is they grew and developed out in the field, sunshine, rain, air. Now they're inside a wall, clay, lack of air, and it's not the same environment. And so initially they wake up, I think, and they start to do their thing, and that's where you get the temperature. Metabolism is same as combustion, okay, but then it's like they can't mutate fast enough to change to function in this environment. They're starved of oxygen, and they got this clay stuff, which isn't normal to their environment either, and it just shuts down.
What does rain do to the exposed walls?
Exposed walls?
You said you wait for 3 months?
Right.
Rain.
The roof has to be on the house before you infill the walls. And they're designed with overhangs. And you can get some rain directly on the walls. And because of the clay, it sheds the rain.
How do you stomp down on the straw clay mixture if you've got a roof on?
You
Do the walls?
the last sheet on the roof is temporary. You just take it off.
I gotcha.
Okay, now you put it back on. Put the tar paper on the roof. You're ready to go.
You still have the hollow tube when you're stomping on that? Because I know your density is lighter, so.
The straw has some if you get in there and stomp on it, and if you don't mind a little clay, you can experience that, at the demo. You feel this sponginess. That's that resiliency that tube has, and all the fibers. So
you're keeping your density down, even after stomping, you just kind of bounce back a little bit.
right. There's some sponginess there, and when you're up there and you're standing on that and you're saying, gee, is this ever going to pack in? Because it just keeps, it's got that sponginess. And then you take it off, it's like, oh my, yeah, it does. This is that same graph. It's just a 7-day average. Okay, that's just to show you how, wham, it just all of a sudden it goes away. It doesn't last. Now this is data that was taken on a 12-inch wall. And also it was taken on a wall sample that has even less clay in it than what our standard is. This is like 10 pounds per cubic foot. We don't ever make those walls. Reason is that when I looked at them, it's like you can tell you're starting to get out of that optimum window. You don't have as much integrity in the wall. So we like to be 12, 13 pounds per cubic foot. It's the sweet spot. The standard wall is 12 inches. That's what we started with. But there's some advantages to going a little bit wider. One is it's a lot easier to stuff the wall. You could maybe get a electrical tamper, if you want to do it, and reduce the number of people you need in order to do the infill when you do it. And it also, of course, gives you more R value. As Lou was saying, 20, 25 for a wall, which is plenty given you only lose, 15 to 20% of your heat through the wall. What this is a 14-inch wide wall section. It's the one that's laying over there on the ground that you can look at. And I've got the dotted line, that's the ambient temperature. And then you have the dark line, that's the temperature inside the center of the wall where you're going to have the most heat during the drying. And then you see the two sets of dotted lines. One's the ambient temperature and the other one is the temperature average, the 7-day average of the heat. And without going into you can't read the bottom here, but again it comes out in about 7 days. You get down to here where there's only a 4-degree change. That's within the ability of the equipment to actually measure differences. So when you get down to there, it's like, well, the ambient and the interior of the bale, equilibrated. There is no activity. And so as you look at that wall section, you break it open, you look at it, it's like, yeah, nothing happened. That's the 14-inch straw clay wall section. It's the interior. I've taken a chunk out of the sample and broken it open. If you look in the middle, you can see it's a little bit different in color right in the middle, right? Well, it's been a year. We made this at the MRA last year. And when you broke it open, you stick your hand on it, it's damp. It's not dry yet. It's been a year. Well, that's a 14-inch wall instead of 12. But the amount of moisture left and the rate at which it comes out of the wall is so low that it doesn't matter, as long as you haven't put a plastic barrier in its way. It'll just dry out. It's going to take a little longer than the 12-inch.
Your 12-inch wall is an R12, R20.
Yeah.
What is this?
Well, it's actually when you finish the walls, it's more like an R21, 22. This would be an R25.
Gain 5.
Yeah. We're still looking here at the drying of the wall. This is some more experiments. What I have here is 2 sections. One's straw only, and the other one is straw clay at 13 pounds per cubic foot, which, by the way, is still 6.5 pounds per cubic foot straw. It's also 6.5 pounds per cubic foot clay. It's equal weights. And that's what they look like after they dry. Now, remember what we talked about with clay? Really likes water, right? More so than straw. Well, the straw ought to dry faster then than the straw clay. Well, it does. Okay, straw only is the blue columns, and you see September and October, they're both higher than the ones that are maroon. And that's because the clay holds on to the water more so than the straw. And I just wanted to, actually see that myself. Always being a little bit particular about it before I spend a lot of money and build a house. Now, microbes, in order to grow, they need water and air, heat, and they need some kind of food, organic material. The thing we try and control, of course, is the water. And here's some data that says that clay helps do that. So they have a box, 80% relative humidity, and they have put straw in there, and they find out it gains 18% by weight. That's the moisture it gains. If they put straw clay in there, what happens is it gains 2 to 4%. Okay, it gains a whole lot less. So that shows how the clay protects. But I wanted a more functional experiment, so I took sections out of a couple of my wall sections, and I laid them out on the driveway. Again, they both have the same amount of straw in them, at the same density, but the one has clay on it. Here's what happened. I weigh them at time 0, of course. That's just the weights they were. I call that 0. Had a 1-inch rain, and the straw only, which is the maroon now, and the straw clay is the blue. Well, the straw only, gained a lot more of the moisture. And that can be a little bit confusing, right? Clay likes the water better than the straw. How come the straw's got more weight here? Well, remember, clay also, when it gets water, it forms this complex that forms a barrier to further water penetration. Straw doesn't have that. So it absorbs more water than the clay, even though the clay has a higher affinity. So now, 2-inch rain, well, now we've really got a difference. So each time it rained, the next day or the next evening, whenever the rain quit, I'd go out and weigh them. So now I got the data I want, I kind of forget about it. And it rains again, and I should get those off the driveway. I don't think the neighbors like the looks of it. It's new development. Guys putting this strange stuff out there. Well, I go out there and I weigh them, and lo and behold, the straw clay one weighed the same thing it weighed when we started. Clay protects the straw from water. It dried out. This is, it didn't take very long. So that's why we use clay on straw. It's because everybody wants to keep their house dry, but if you have an accident, you want some insurance. The clay gives you that. And you don't have to have that much. If you look at the straw only one, this is what they look like after 3 rains and dried out. You see there's a wet spot on the straw only. It's like, gee, it's slow to dry out. Well, that's not accurate. Microbes are feeding on the straw. Okay? Combustion is what? Carbon dioxide and water. They're generating water at a fast enough rate. They're keeping the thing wet so they can continue to grow on it. That's what happens when you get a wet spot and you don't have any protection. So, there's a real danger to having wet straw that doesn't dry out right. Controlling the R values on the job site. First of all, I had to figure out exactly how do you make 13 pounds per cubic foot wall. Well, as it turns out, 30 pounds of straw and 58.4 pounds of water and 20 pounds of clay will get you this 13 pounds per cubic foot in this wall section that I used, that you saw a picture of, 2 by 2, 12 inches thick. Now, it's 8.4 of those pounds of water are actually what the clay has. the other 30 pounds of what the straw absorbs. And it absorbs it every time. And that becomes a very important, valuable piece of information. We know that the R value is directly connected to the density of the wall section. So we've got to control how much clay goes onto that straw if we want to control the R value at the job site. So to begin with, of course, we need to know, as we talked about before, how much clay is in the subsoil, because that's the part of it that we want. We also, in order to get that R value, we need to know what volume of that actually ends up on the straw. And of course, because we're putting water on the straw, we need to know how much clay is in the water. So those are the three things that we have to know. How much in the subsoil, how much clay is in the water, how much clay of that clay slip actually goes on the straw. And we have to do that on the job site. Well, this allows us to decide how much of that subsoil actually ends up on the straw. And it's just a calculation off the lab analysis. And knowing how much of that we can actually get rid of. So, we actually screen out the rocks and some sand, and we have some settling out sand, and we know that the clay, all the silt, and a little bit of the sand end up in the wall. And from that we can select the percentage, and then we know how many pounds of dry material we need to get into the water that we have in a tank. The tank has, gallon marks on it, and since it's a volume measurement we're working with, we put that dry in there. We know what level on the tank we need to get before we quit adding clay to it. And basically, if you take a 5-gallon bucket of subsoil that's been shredded, we use a shredder to get rid of the initial larger rocks and to get large surface areas. If they have a 5-gallon bucket of that, half of that, about 55% of that is air. 45% of it is actually subsoil. So we know how much subsoil we have in the clay slip because we have the markings on the tank. And then you remember, we know that straw is going to absorb 30 pounds of water. And we know how much, that when it does that, if you take some and you twist it really hard, we call it the cigar test, a little bit of water will come to the surface. So all we do is we stand at the end of the mixer and we look for that condition where if we twist it, we see a little bit of water on the surface. Then we know that we've got that 30 pounds of water on that 50 pounds of water on the 30 pounds of straw. And we know how much clay is in that water, so then we have our density. So we can control, 13 pounds per cubic foot, we won't be off more than a half. And for the R value, that's going to make very little difference.
So are we at about half a bale for that? For 30 pounds?
A small
typical-
a small bale is around 30 pounds.
It is?
Yeah.
Smaller ones.
Yeah. But you don't need to know.
So those are less than 3 foot.
Yeah, I think they would be. You don't. I mean, you can just throw the straw in. You don't have to know how much straw
Okay.
you put in. Because you're going by the cigar test. You've controlled
Okay.
the ratio of clay to water, or subsoil to water, and the straw controls how much water it takes up, because you're going by that test. So you automatically know how much clay you put on that straw. So there's a cigar test. You really have to twist it pretty hard, and you'll see a little bit of, water beads forming the surface. That's where you want to be. This is some of our mixing equipment. the lower right, you see a shredder made by Royer, and we have a mixer there. I don't think that's my best side, but that's the dispersing blade. I'll bet you haven't seen one of those. Okay? It's made out of urethane. Why? Any kind of a metal blade you put in there with all that sand, it gets sharp like a razor blade. It'll just wear the blade right out. Two things have to happen in order to disperse clay. Clay is not easy to disperse. Okay? You need a shear plane. You need a surface that's not moving and one that is moving. So you can do this. So you can transfer that energy and pull those particles apart. Blue clay is especially tough. Well, two things need to happen. Another thing needs to happen besides that. Besides the shearing, you have to have pumping, because everything that's in that water has to go through that zone to get dispersed. So this blade will do that. Those cups on that blade do the pumping. But the surface of that blade is only an inch off the bottom of the tank, maybe an inch and a half. And you're turning it at about 1,500, 2,000 feet per minute tip speed. And so in real time, on a construction project, you can make enough clay slip to keep up with the demand. And you got to do that if you're going to be a contractor and use such a process, which was our point. And our goal is to develop equipment that give you real-time performance. The blade's $450. It'll last for a number of houses. In terms of cost, it's nothing. This is some more of the equipment. We use a mud pump for transfer. You see our screens there that we use. We transfer out of the black. You saw the black tank. It's the diameter of the tank has to be ratioed with the diameter of the blade in order to get this fast dispersing. And we start out with less water because we want it thick, because you have more shearing action, more energy transfer if it's thicker. Okay, then once we get it dispersed, we can use a larger tank to put it through the screen into these 100-gallon tanks. We will then add water, so we dilute it down to the ratio we need of water to clay, so that when that 50 pounds of water goes on the straw has all the clay it's supposed to have. Now, if you short yourself on water, what happens is the straw sucks it up. As soon as the straw sucks up all the water, the clay goes down. And what you find is some of your straws doesn't have any clay on it. You have to have the water there for transport. You have to have enough that all the straw gets wet, because that's the only way all the straw is going to get clay on it. He's screening it right there. This is the mixing head we use for the second step dispersing. In the first step, you can have little globules of clay undispersed yet. And so we do a finishing dispersing. This is called a squirrel cage mixer. Again, we're looking for a shear plane. Most mixers do a lot of movement. People look in the tank and a person says, geez, that's really being mixed. Well, it's being really moved. It's not being really dispersed. So a squirrel cage mixer has all these fins on it. It sucks in water from the top and the bottom, and it shoots out through the fins. So the water is moving through the fins radially. The fins aren't moving. We have that surface again. Here's the fin. It's not moving. Water is going by it. We have that shear plane again. Same ones we had in the bottom of the tank. So now all those little particles, clay clumps that aren't dispersed yet, they get dispersed. That's what it looks like. Home Depot sells one you can buy for, it'll handle a 5-gallon bucket or maybe 10-gallon. The bigger ones you got to go to companies that specialize in mixers. That's the second step dispersing. You have to have some baffles in the tank if you don't want to look brown. To the right there, you see a nurse tank. That's where we pump over. It's our reservoir. So we have it's kind of like a surge system. So you have a little trouble with production. You know, there's stuff there in the tank. You don't interrupt the project. There's the mixer. See, there's a tube that goes in it. There's a mud pump, and there's holes in that wand, and it sprays that slip out onto the straw that we throw into the tube. Tube's turning around. There's nails in it, so the straw is getting flipped around, and that spray comes in there. By the time it comes out the other end of the tube, totally mixed. You can keep 20 people.
Water that drains out, I mean, every water that you put in is all absorbed.
There's no drainage that comes out. No, there's no water that runs out the other end. It's just
But you know you got enough.
right. You do the cigar test, and if you're not, you tell the guy too dry, and of course he's got to adjust the valve up front, and then pretty soon he gets into a rhythm. You know, the valve set here, he's throwing at this rate, everything comes out just the way you want it. So there's the production end going into. Well, they use large boxes. A skid loader typically is what we use, and it's carried over to the house where it's stuffed in the walls. There, we're stuffing a wall. The slip forms on the outside, you can see there. People are inside pushing it down. Okay, the last here is that in terms of, okay, here's what can happen. I mean, here are the things that you do in order to avoid having mold issues, okay? We're talking about, you know, it's kind of like operating conditions. It's like the lawnmower thing. You got to set it right if it's going to work right. You don't want the initial wetness too high. That's not very dangerous because if you put too much excess in, it just kind of runs out the bottom. But you don't want to over-wet it. You don't want re-wetting too frequently from rain. In other words, you can stand some rain, but you know, you don't want to have a lot of rain, and you certainly don't want to have a case where you don't have a roof on. You're not ready to stuff the walls if you don't have the ability to put a roof on when they're done. You know, that day they're finished. The humidity levels due to weather or enclosure. Okay, so we haven't performed this out in Oregon, you know, on the coast where it's very humid and so on, so we don't have test data for those conditions. Well, you don't want to make those conditions by putting in the windows and the doors and shutting them. So those have to stay out until you get some dry down. You can't use subsoil that's got any less than 40% clay. You'll sacrifice the integrity and the advantages that we just talked about. You don't want any dirt in the straw. You don't want any dirt in the clay from work at the job site. If you've got nice black soil there, you want to have a barrier between the clay that you're piling on the ground because you don't want that dirt to get in the clay and then get in your wall because that's just food for microbes and you're not into feeding them. You don't want uneven clay coverage because you didn't have enough water. You don't want immature plant material. You don't want green stuff. Throw it out. You know, if you got a bale just got a lot of green stuff, set it aside. You don't want really high levels of dormant microbes. That's what happens when it rains and the microbes start to be active and they multiply and then it dries and then they harvest it and then they bale it. Now it's not bright anymore. You don't want to put that in there. You're putting in a lot of extra microbes. You don't want poor quality straw. Now, what we would really like to do is have a specification via a tissue test. In agronomy, you can tell quality of things by looking at what the mineral ratios and contents are. We need some more grant money. The operating window, got to have a roof, just as a regular house. If it's not roof protected, then you're not ready to stuff it. The forms need to be left on a minimum of an hour. Typically, 2 to 4 is better, and greater than 4 hours increases the risk of surface white mold. Now, typically, the forms are taken off at the end of the day. We have left them on overnight. It's not a big deal. the white mold disappears. It's just right on the surface. It's a very temporary thing. If you want to go away real quick, spray it with vinegar or vinegar and peroxide, and it's gone. You don't want to reuse forms that are moldy. That discoloration is simply microbes that are dormant. As soon as you press them up against the wet material, yeah, they're going to wake up and decide to go to work. So you don't want to use old, dirty forms on the studs to make your cavity. We already talked about this. You got to have proper ventilation. So if you do have a lot of rain and the wall's been getting wet and re-wet, you got to protect them. You may need to put some tarping on. Properly designed overhang is the best approach. And we've talked about evenly coating, with the clay. And we have to have adequate drying for plaster.